we're going to look at linear regression in this chapter. So we're going to be using some of the information that we learned in chapter 6 to look further into regression. I want you to take a minute and recall how to describe a scatter plot when you're looking at an association between two variables. This scatter plot shows the speed in miles per hour plotted against the height in feet for 91 roller coasters, and the coasters are described as thrill coasters. I'd like you to describe the association. So if you'll recall, when you describe an association, you need to talk about the direction. So is it positive or negative? The form, is it linear or nonlinear? The strength, and we say strength when it's linear, we can discuss correlation, right? And correlation, remember, measures the strength and direction of a linear association between two quantitative variables. And then we also want to mention any outliers that we may see. So take a second, pause the video for about a minute, and describe the association between the height and speed of these roller coasters. The association, or just relationship, right, between the speed of the coasters and the height I would say is positive because it's sloping up to the right. It's very linear. And I would say it has a strong correlation. What I notice is as the height increases, the speed also increases, which tends to make sense because the higher the roller coaster track is, the faster it's going to go down that hill. So in the scatter plot above, can you imagine a line that would model the essence of that relationship? Okay, if we drew a line, obviously it's not going to go through all of the points. In fact, it may miss quite a bit of them. If we had an equation for such a line, it would be called a linear model. And we could use it to predict or estimate the top speed of a roller coaster given its height. So if we're given X, we're able to predict Y, sometimes accurately, sometimes not so much. Do you think it's possible to draw a line through all of the points? As we just kind of said, no, right? At the best, the line may not hit any of the points, right? So the best line might not even go through any of them. And we're going to talk about that in this chapter. Our goal is to find a line that comes closer to all the points than any other line. Some points may be above the line, others might be below, and others might be on the line. For example, the line may suggest that a 78-foot tall roller coaster would reach a top speed of 44 miles per hour when it actually reaches only 40 miles per hour. If I was to draw, let's say, a line like this through these points, if we were to go to a 78-foot roller coaster, so maybe like right about here, and go up and hit the line may predict that this is going to be about 45 miles per hour, right? 44 miles per hour, but actually maybe it only reaches 40 miles per hour. So models are not always going to be perfectly accurate, but models get better over time. If you think about, car models, like if you take a Toyota Camry in the 1980s or Toyota Corolla, that Corolla is not the same as what it is in 2024. They've improved it over time. So models can improve over time. So sometimes they might not be accurate at first, but the more information we get, the more data we have, we can get a little bit more accurate. The estimate made from the model is called the predicted value. Okay, so that would be the 44 miles per hour. And it's written with a hat over it to distinguish it from the true value, which would be y, right? So in this case, in this example, y hat would be the 44 miles per hour because that's what the line's suggesting the 78-foot tall roller coaster would reach, the top speed. And then the actual is y. Okay, so the difference between the observed, also known as the actual value, and its associated predicted value is called the residual, right? And the word residual is the word residue or leftover. The residual tells us how far off the model's prediction is at that point. The formula to find the residual is E equals y minus y hat. And E stands for error. So we refer to it as like the error term. Not error as in a mistake, but we'll talk more about that later. So we can also just remember it using words, which would be the observed or the actual minus the predicted. Y minus y hat. If you think about it, right? So if I go up to my line, for instance, let's take this point right here, okay? That point that I circled, whatever that y value is, that's my actual point. The line predicted, though, that it would be here. That's my y hat. So that vertical distance there is the residual. It's the leftover. So if I want to find the leftover, I would subtract the actual minus the predicted. And here you would get a negative residual, right? So what does that mean? It means that the line underestimated what it actually was. A line that fits very well, then you can imagine, would have very small residuals. Now what we would do is we would need to square all these residuals, right, to look at the distances, just like we did for standard deviation. But remember, when we did standard deviation, we also got negative distances or deviations. And the way we undid those was by squaring them, right? Now, if that were to happen here, the negative and the positive numbers would cancel each other out. And then we would add them all up. Squaring emphasizes the large residuals. And when we add up all the squared residuals, the sum indicates how well the line we drew fits the data. Okay, the smaller the sum, the better the fit, right? Because we would want those distances to be as small as possible because that means the line got really close to the actual or observed values. For each data set, one unique line makes the sum of the squared residuals as small as it can be. And that line is called the least squares line. It's also known as the least squares regression line. Or LSRL for short. So if you see that in the textbook, it stands for least squares regression line. Or sometimes we just refer to it as the line of best fit. Regardless, we want the sum of the squared residuals to be the smallest, or the least. Correlation, remember that's the letter R, that's your correlation coefficient, can lead us to the equation of the linear model. The correlation, or R, tells us what fraction of a y standard deviation you expect to be from the mean y value if you're 1x standard deviation from the mean x value. In general, moving any number of standard deviations in x moves r times the number of standard deviations in y. So let's take a look at that here in this example. And you can pause it to read it and unpause when you're ready. A scatter plot of house price in dollars versus house size in square feet for houses sold recently in Saratoga, New York, shows a relationship that is straight with only moderate scatter and no outliers. The correlation between house price and house size is 0.76. The least squares line is price hat, so there's your y hat, equals 8,400 plus 88.67 size, and size is x. So this should look very familiar to you. It's basically y equals mx plus b. In statistics, though, remember, we're going to write it as, and we'll talk about this, y hat equals b0 plus b1x. Or on your calculator, it's a plus bx. Okay, so what's important is here, if you think about y equals mx plus b, m, that's your slope, b, that's your y-intercept. And I apologize, my marker is acting up here. Okay, and again, we'll talk more about those. So you go to an open house and find the house is 1 standard deviation above the mean size. How many standard deviations above the mean price would you predict it to cost? So if I go back to what I just wrote down, moving any standard deviations in x moves r times the number of standard deviations of y. So what's r? Well, it told me that r is 0.76. So what that means is you should expect the price to be 0.76 standard deviations above the mean. Because in general, moving any number of standard deviations in size would move 0.76 standard deviations in price. You read an ad for a house that's 2 standard deviations below the mean size. What would you guess about its price? So below tells me it's going to be below average, right? So that means you should expect the size to be 2 times 0.76 or 1.52 standard deviations below the mean. A friend tells you about a house whose size in square meters, he's European, is 1.5 standard deviations above the mean. What would you guess about its size in square feet? Okay, so if you'll recall, no matter how the size is measured, the standard deviations will not change. So the home is 1.5 standard deviations above the mean in size, no matter how it's measured. Because the units don't matter. And we had kind of discussed that back in chapter 6 when we were talking about correlation. And then D, suppose the standard deviation of house prices is $77,000. How much more expensive than the mean price would you predict for the house in part 1? That's 1 standard deviation above the mean size, right? So $77,000 is equal to 1 standard deviation. So moving 1 standard deviation in size, right, or $77,000 in size, should move 0.76, remember that's R, your correlation, standard deviations in price. And you can think of it like this. That would just be 0.76 times 77,000. Because think of it as like 76% of 77,000. And that's $58,520. Okay, that's the end of this video. Please come back for the next part where we're going to look closely at our linear models and how to construct them and pull them apart and interpret what each little piece means. Have a great day, everyone.